Okay, you'll notice it says this weird S shape. It's called an elongated S, or the Latin term for it is summa. Okay, because you're actually summing up the area when you're finding antiderivatives. You don't really need to know that. What you need to know is this means find the antiderivative. Okay, this is what I was talking about before. Like, some of this notation is new, but as soon as you see that, a light bulb should be going off in your head. Antiderivative. Okay, and then we have a dx over here. Okay, I know there's the secant x tan x in the middle there, but I'm ignoring that for right now. You'll notice we're multiplying by dx. Okay, this is different than when we were dividing by dx when you did the derivative. Okay, so if you think of d over dx, and let's just say we had, I don't know, secant x tan x, the opposite of this would be this, what's written in the problem right there. Okay, so I really want you to make sure you understand the notation on this, because it does come in handy later on. Hold on, something, oh, there you go. Okay, so that means antiderivative. So essentially what we're doing is the antiderivative of that secant x tan x. Okay, does anybody have any ideas on how to do this? There's numerous ways you can solve this problem, especially since it's multiple choice. Hint, hint. But does anyone have any ideas on how to do this? You can just throw out ideas. Yes. Okay, you could take the antiderivative. One thing that I'm really pushing for on this is like the fact that we're going backwards on this. So what has a derivative that's secant x tan x? It's part of your memorization list. Does anyone remember? People at home? There's a specific thing where if you take the derivative of it, you get secant x tan x. The derivative of secant x is equal to secant x tan x. So if I'm doing the antiderivative, you have to know your derivative rules, otherwise you wouldn't be able to go backwards. If you know that this thing right here is the derivative of secant x, so you're going this way, if you go the other way with the antiderivative, that's the answer. Okay, except you'll notice that there's a plus c. The reason for that is if you did the derivative of this secant x right here, let's just say, let me rewrite it really quick. So say I did the derivative of secant x, but I added a constant to it. Let's just say I added 3. Okay, you are still going to get the same answer because the derivative of 3 is 0. So if you look at the answers over here, you'll notice it says secant x plus c. You always have to have a plus c when you do antiderivative. So I would write that down or just make a mental note of it. You always have to add a constant. And you don't know what the constant is. It can be 3, it could be 3,000, it could be 1, it could be 100, it could be negative pi, it could be anything, as long as it's a constant. So there's no variables in that. So that's why they all have plus c. If you forget a plus c in the free response, usually they don't try to trick you with the multiple choice on AP. But if you forget that on the free response, you will lose an entire point. Okay, some of these points are worth, like, some of the problems are worth like 3 points. You'll lose an entire point just for the plus c. Okay, it is really, really important that you don't mess that up. If you mess it up on one of my tests, you will actually get a C because it's a minor calc error. Okay, and you might be thinking, wow, that's really rude of you. Why don't you just do a B? Why do you jump from an A to a C? And the reason is because my tests don't count anyway, and I really want to push that point across that it is a minor calc error if you do that. Okay, you have to have the plus C. Sorry, I'm not on assignment here. Okay. There is a comic that I put on my website under Unit 4. I believe it's Unit 4. Or, yeah, I should put it here on the Unit 4 page. Hold on. Let's see here. Maybe it's here. So here is, this is, what is the name of this comic? I forgot. But he only does like math stuff. But he made one of a plus C basically as this kind of a joke. So it says right here, does your math homework look like this? The antiderivative, remember, this means antiderivative, that x to the third dx. Okay, the antiderivative of x cubed with respect to x. They did the antiderivative. We don't really need to worry about that. But they forgot to do the plus C. So the teacher wrote in, don't forget the C, 1 out of 2 points. So they just lost 1 point. And then it says, you keep forgetting plus C? Yes. Well, stress no more. Introducing the plus C stamp. Easily attaches to your keychain or necklace. Awesome. Red ink pads available for teachers for grading. And it's just making fun of the fact that people mess that up all the time. Okay. Spiked math, that's what it's called. Spikedmath.com. But he has like a lot of like jokes about stuff, and I saw this one. I gotta add it to the class. And what? Oh, so they're adding something to it. Does that make sense with the plus C, everybody? Okay, I know I could have just wrote a bunch of notes down and said do a plus C, but I kind of want to just throw you in the deep end because we're just going backwards of what we've just done. This whole unit is just going backwards of what we've done, and hopefully you see that. Okay. So looking at this problem, you might go, oh, I could never solve this. But once you actually know what these symbols mean, you could solve it. It just means the antiderivative, you're going backwards. One thing you could do, and I highly advise doing this if you are just one of those people that likes looking at the answers, you could have done the derivative of every single one of these and then seen which one of them is actually secant x tan x. You can do that worst case scenario. Obviously, it would take a little bit longer if you did that. So if you make an educated guess and go, oh, secant x tan x, I bet that's secant x, and then you do that derivative. For fun, I'm actually going to do that derivative really quick just to kind of show you. So we're going to do the derivative of secant x, which is equal to the derivative. You don't have to write this down because I know we've covered this before. But that's the derivative of cosine of x to the -1 power. Okay, so now if you do chain rule on this, you bring the negative down. So it's going to be negative cosine of x, quantity squared, or to the -2. That's embarrassing. I'll just put it out here. -2 power times the derivative of cosine, which is negative sine of x like this. Okay, the negatives are going to cancel here, and you're going to be left with sine x over cosine squared x, which sine over cosine is tangent, and you're still left with one of the cosines on the bottom. So that's the secant x there. Okay, so if you wanted to, you could do all the derivatives and go, oh, that's the derivative. So then going backwards, it's the antiderivative. I would not put all your chips on that, though, because if it's a free response problem, you're not going to be able to just do the derivative of everything because there is no multiple choice. Right? Questions on this first one? Everyone's good? Super easy? All right, next. We talked about this a little bit yesterday, and I said the great thing about antiderivatives is it can help you find the area of a non-basic shape. Does everyone remember that graphic I showed? This one right here. So as long as you define something with a function, which you can if you have regression, you could make anything, any points of data into a function. But antiderivatives help us find the area of a non-basic shape. So not a circle, not a square, not a rectangle, not all those things that have equations. But what's cool is if you actually use integration, you can see where those formulas come from. It's kind of cool. I'm sure some of you noticed this already. The area of a circle is pi r squared, and if you do the derivative of that, you get the circumference. Right? And if you think about a sphere, 4/3 pi r cubed, and you do the derivative of that, you get surface area. You don't need to know that, but it's just kind of cool how you can do that with integration. We're going to have a non-basic shape right here. Okay, it says what is the area of the region, and area being the key word. A light bulb should be going off in your head right away, and you should be thinking antiderivative. Okay, so I would write that down in your notes too. Anytime you see area, antiderivative. Okay, and it says the area of the region in the first quadrant bounded by that graph and x equals 2. Okay, we're gonna sketch this graph, and I'm just gonna kind of show you. You don't need to actually know exactly what the graph looks like, but it does help a little bit to kind of get an idea. Okay, first thing I'm gonna do is graph this x equals 2 line, just because it's super easy to graph that. We're just gonna say it's right here. X equals 2. By the way, a lot of times AP does everything in the first quadrant, which is nice. So you don't have to worry about like negatives. I should say this now too. The area of a region, there is a thing called signed area where you can have negative area. We'll go over that a little bit later. But what's awesome, if it's in the first quadrant, it's always going to be positive. But if you imagine like some graph that does like this or something like that, this part would be negative and this part would be positive for the area. It's called signed area, but we don't need to worry about it for this because this is e to the x over 2. And so it just kind of does this. Okay. You have to kind of, I mean, a little bit, it helps if you know what the parent function looks like for that. Now, is that exact? No. Does it need to be? No. Okay. What is the y value at x equals 2 for that graph right there? Anybody? Just yell it out. What's this y value? Because I want to know the coordinate here. E. E. Very good. Okay. You put 2 in for x here, and you get e to the 2 over 2, which is e. Okay. Do you need to know that? I don't think so, but it's still good to do. Okay. It's in the first quadrant, so you don't actually, so what the area we're looking for is this part right here. You don't need to worry about anything in the other quadrants. So even though I drew the red like over here, you don't need to really worry about that so much. But if you notice, this is a non-basic shape. Okay. Kind of looks like a triangle, but like, what is that really called? You don't really know. But what's cool about integrals is you can define it based on integrals. Okay. Integrals, again, antiderivative. Integration, antiderivative. Integral, antiderivative. Think that every single time. Math's a language, and the second you can start understanding that stuff, tying it to stuff you do know, it's going to make it a little bit easier to understand. All right. Any questions so far on what we're doing? You do not have to draw this if you don't want. Some of you can just draw it in your head. That's fine. This is just a part of the lesson, so that's why I'm drawing it out. Okay. The formula for this, or the expression that you would use for this integral, because we're finding the area, is still going to have one of those summas. But because this is actually the area, we're using the antiderivative to solve this. Okay, so we're using the antiderivative, but it's not just find the antiderivative. Number 3, the first one we did right here, was just find the antiderivative. Okay, this one says find the area. So you have to use the antiderivative, but the antiderivative is not the answer, but you need it still. Okay, it's kind of like you can find the derivative, or you can find the derivative at a point. Here we're going to find the antiderivative, but we're going to use it to find the area, if that makes sense. Keep repeating myself, I'm sorry. Okay, so this area, and if you want, you can write a equals. It's up to you. But you have to integrate it from 0 to 2. So what we're doing is from 0, because that's where this thing starts. The area is going from 0 to 2, and that's in terms of x. So x is 0, x is 2. Okay, and we're finding the area of e to the x over 2 with respect to x. Okay. One thing that students ask me every single year is, where does the dx go when you do the antiderivative? Okay, so if you notice up here, we did the antiderivative of this secant x tan x, and the dx just disappeared. It doesn't actually disappear. It's part of the actual formula. We're used to stuff where it's like d over dx of x squared. That means the derivative of x squared. This is in front of it, and it's all together. For some reason, with antiderivatives, they don't write it like this. They don't write the integral of x squared, which would kind of make sense if you think about it. I mean, you could do it that way if you wanted, but instead they sandwich the x squared in the middle with the dx over here. So the dx doesn't go away. It's this means antiderivative with respect to x. Okay, I'm going to go into more specifics of what that dx really means and where it comes from, just not today. It's not really that important. But people always go, where does it go? Why did it disappear? It's part of the antiderivative. Just like d over dx, you need that dx for that. Okay. Another way of looking at it is if you do like 1 + 1 = 2, where does the plus go? It's part of the 2 now. Okay. This dx is going to be part of this antiderivative. Okay. We need to do the antiderivative of e to the x over 2. Okay. So what I would do for this is just thinking about it. What if you did the derivative? What would it equal to be? Here, let me rewrite this. The derivative of what? So I'm going to just put a little question mark here. The derivative of what is equal to e to the x over 2? Okay, this is going to be our first antiderivative rule, by the way. But any ideas? Some of you can probably just figure it out by like guessing and checking in your head and trying different things. Any ideas? And we're just going backwards on this. I'll give you a couple minutes for this. Someone's got to know it. Okay, hold on, let's go. 2/3 e to the what? No, not 2/3. Oh, what is that? What you? Here, before you answer, try whatever you think your answer is. Do the derivative of it and see if you actually get it. Go ahead. e to the 3x over 2. So if I did the derivative of this, wouldn't you get 3 halves e to the 3 halves x? Oops, that's embarrassing. Yep, it's okay. He was kind of on the same track with that. It's not power rule, so you're not going to want to use power rule for this because it's exponential. I got hints on hints here, so if no one's going to get it, I'll drop a hint on you. Okay, ready? Watch this. What's the derivative of e to the x over 2? You have to know this. This is chain rule.
E to the x over 2 times 1. Or just times 1.
Well, what's the derivative of x over 2?
1.
Come on, what? 1/2, thank you. Everyone see what I did here? That's just chain rule. Like, you should know that by now, no offense, if you're not getting this. But it's just you multiply by the inner layer. The inner layer's derivative is x over 2. If you rewrite it to be 1/2 x, the derivative of 1/2 x is 1/2. Oh, did he actually write the final answer in the chat? Okay. Did he write 2e to the x over 2? Okay, that is correct. Very good, Charlie. All right, check this out. Another thing you could have done is, look, I want to have e to the x over 2, but I have a 1/2. So what do I need to do to both sides here? Fine. To get this to just be e to the x over 2, how do I get rid of the 1/2? Multiply by 2. So check this out. And I know Charlie just said this, but it's 2e to the x over 2 because this cancels. And now you're left with that orange that we wanted. And if you don't believe me, try doing the derivative of 2e to the x over 2. And you will get e to the x over 2. Okay? I know this is complicated because we're going backwards, but you do have the ability to do this. Okay? You do have all the knowledge that you need. Are there any questions so far? Does anyone think this is fun versus me just lecturing, like you're trying to figure things out? Is that okay that we're doing it this way? Okay. All right. So now we know that antiderivative. Thank you, Charlie. It's 2e to the x over 2. Why did I not hear that, though? Volume's up. Do I have the chat open? No. Why did I not hear that? That's so annoying. Yeah, very good. The fact that you got that is quite amazing. Yeah. And again, because I'm actually giving you problems you've never seen before. Anyone can do a problem they've seen, but like to just do one like this is just crazy. All right, so we have that antiderivative. By the way, you could just guess and check. I mean, some of you factor that way when you factor quadratics. You'll guess and check and try to figure out the numbers. You can do that with this too. Just go, oh, I think it's 2e to the x over 2. I'm going to do the derivative really quick. Oh, it is. Okay, cool. And then move on. The rule, though, is this. Check this out. You're going to want to write this down. Okay. If you have, where can I write this? It's not going to get in the way. All right. If you have a function that you're doing the antiderivative of, and there is a constant buried somewhere in there, like x over 2, there's a 1/2 constant with that x. Okay, you have to have the dx, by the way. And by the way, if I ever forget the dx or if I ever forget the plus c, call me on it. No, because we're only doing the derivative. And also the area doesn't have the plus c, but we're going to go over that in a little bit. But good call. See, I like that. Check me. That's good. Okay, this is the rule. What you can do, and you probably have already noticed this from the rule already, just based on the example problem we just did, it's equal to 1 over k of f of kx plus c. Embarrassing. Okay, it has to be linear though. That's the main thing. X over 2 is linear, right? It's not x squared over 2. If it was x squared over 2, you cannot do anything with it. So it has to follow this specific rule. Kx is linear, okay? And really, it could be kx plus a constant as well. So let's make this rule a little bit better. You can have some other constant here. Let's just say I don't want to do, I'll do lowercase c, I guess. No, I'll just do a, okay? Because it's still technically linear. Kx plus a is still linear. The derivative of that a would go away anyway. So this is going to have to be kx plus a as well. Usually it's not written with the plus a in there, but trust me, you can do it that way. There is another way of doing this too that I'll show you, and it's a lot longer than using this rule, but I'll just show you for fun, but I highly advise not doing it. I don't show my regular non-AP calc students this because they just do it even if it's not linear, but since this is AP, I will actually show you another way of doing this that takes a lot longer, okay? Long story short, we're not done yet here because we have to still finish this problem out. Now that we have the antiderivative, I'm going to throw it over here, and we have 2e to the x over 2. There is no plus c because it's area. We're going to talk about that in 1 second, though. It'll make sense soon. And then you do a half bracket here. And we're integrating it from 0 to 2. What this means, that bracket, it's not exponents, it's not subscripts, because it's on the bottom here. What this means is you're going to have to do 2e to the 2 over 2. So I plugged in the 2. And then you're going to subtract when you plug in the 0. E to the 0 over 2. That's what this means. Remember I told you everything in math with the notation is a language? When you see that, that means plug in 2, plug in 0, and subtract the 2. And you plug it in for x. You have to plug it in for x. Okay. So we are not done yet, obviously. We got to simplify this out here. So it's going to be 2, thank you, yep. So it's going to be 2e minus 2, which is a. Holy moly. So let's break this down. When you're trying to find the area, you need the antiderivative. You find the antiderivative, you plug in the limits of integration. That's what they're called, the 0 and 2 in this case. You plug in the 2, you plug in the 0, and you subtract. That tells you the area. Okay. If you want to know why this works, I have an awesome video that explains it. Do you need to know that for the class? Absolutely not, because it's absolutely insane, but it's awesome. Okay. Now, even though this is a non-calculator problem, I do want to show you how to do these on your calculator because there are certain problems where you're going to have to use your calculator to solve this because the antiderivative doesn't exist, which is insane. And when I say it doesn't exist, I mean it doesn't exist in closed form. You can only define it with an integral. It doesn't actually simplify to anything. But this is going to get crazy. Crazy awesome. All right, check this out. We're going to do, well, I'm going to show you first. Let's go to the home screen. So we're going to do math. Instead of math 8s, we're going to do math 9. Unless you have an old calculator, no offense, check out my screen. It kind of breaks it down for you there. If you have an old calculator, I'm going to show you how to do this. But I highly advise not using an old calculator. It's the same steps as what we're doing. It's just a little bit different. Okay. Now, what's cool about this is it's a template for exactly the equation that we were looking for. So put a 0 in there, put a 2 in there, and then we're going to do e to the x over 2. And then we're going to put an x there, hit enter, and you get that. Okay. Does anybody want to bet if this is 2e minus 2? Very good. Boom. Okay. So that's one way of doing this. This is probably the fastest way, but I do want to show you this other way too because it's kind of cool. In your y equals, put the equation. Don't put the antiderivative, by the way. The calculator does all that for you. Okay, so e to the x over 2. Graph that. Okay, now we're actually going from 0 to 2 on this. So what I want to do is go window 0 for the x min and 2 for the x max. I feel like I'm going too fast. Zoom 0. Okay, it kind of looks like my drawing. It's a little triangle. If you had to estimate it, you could use a triangle formula for it. Half base times height, right? If you really wanted to. Now check this out. Second trace, now do 7. If you look at the 7th, it's actually the integral of f of x dx. And then it says lower limit, hit 0. Upper limit, hit 2. Check this out. It actually colors it in for you. Isn't that amazing? And then it gives you the answer on the bottom. Oh, yeah. Sorry. I know. I'm like hyped up. I'm sorry. All right. Do you have the y equals in there?
Yeah.
Okay. And then go to window. Did you change the x min and x max to 0 and 2, respectively? Okay. Once you do that, hit zoom 0, and it fits it to the screen nicely, so it's pretty. You do not have to do it this way. If you wanted to, you can just print it like this to the screen and still go 0 to 2. It just looks a little bit different. I'll just show you really quick. So 0 to enter, and it just still colors in the area there. But I don't like that. Oops, that's embarrassing. Hold on. 0, enter 2, zoom 0. Okay, ready? Second trace, 7. Okay, lower limit is 0. Upper limit is 2. Hit enter, and then the answer's on the bottom there. Okay. Now, if you have an old calculator, I'm going to show you how this looks with the old calculator. I might mess this up, though, so just bear with me. I have to turn this math print to classic. Okay, so old calculator people, you ready? Is there anyone else that's old? Oh, you have old calculator? Oh, there you go. All right, math 9 is still the same thing, but then it says function integral, function int. Okay, if you've taken coding, it's, never mind this. People haven't taken it. All right, first thing you have to do is put in the equation, or the expression, I should say, that you're trying to do the integral of. Hit comma, and we're doing it with respect to x, comma, 0, comma, 2. Hold on, though. This might actually, okay, it did work. Sometimes I do 0, 2, and then x, but it's x, 0, 2. Okay, as you can see, the new calculator is much better. No offense. No offense. When I was a kid, they only had this. But if you want to use this, all right. Okay. Now this is good when there is no closed formed antiderivative. This is a closed formed antiderivative. If you notice, I did the antiderivative and there's no integral anymore. Today we're actually going to go over a problem that you can't do that. It doesn't break down to anything, which is crazy because you can do the derivative of anything, but you can't do the antiderivative of everything. Why? Why? It's just crazy. Like whoever invented the universe made that a rule, so far as we know. It exists because you can still graph it. You just can't simplify it. It's like a fraction you can't simplify almost. In a way, like it just doesn't break down. You'll see when we get to it. All right. Is everyone okay so far? Okay, we are still going to do a deep dive in each individual section too. This is just an intro for this. So, all right, using substitution. Okay, using the substitution, u equals the square root of x dx is equal to which of the following? Okay, this is going to get really nutty. This is actually the hardest section of the entire unit. Okay, so if you can get through this, you can get through anything. Basically, what we're going to do is called chain rule in reverse. Okay. Because everything in this unit is in reverse from what we've been doing. Sounds like what? It is, but once you do it, you're good to go. It's kind of like implicit differentiation. Like it was probably complicated at first, but then once you got the hang of it, you were good. I'd say this is a little bit easier than implicit. Okay. All right, here we go. So it says using substitution. So this one right here, you cannot use an integral rule for it because it's not one of the other rules we've had in reverse. Okay, some of you are probably trying to do this in your head with chain rule, and that's amazing. I'm sure you can do it. A lot of people can do it here because You see the inner function is the square root of x, and when you do the derivative of that, it's 1/2 x to the negative 1/2, which is the division by square root of x. But it doesn't matter. Let's act like we don't know that. But you do know that, and you want to go ahead and just try the problem by all means. So what we're going to do is I'm just going to rewrite it really quick here. And you cannot do, there is no rule for this. Okay, there's a rule for e to the x, the derivative of e to the x is e to the x. But there's no rule for when it's something crazy like this, and there is no such thing as a reversed quotient rule. Okay, there is a reverse product rule though. So I guess there, in a way you could move that in to be a quotient rule, but there is no reverse quotient rule. You'll learn about integration by parts in Calc 2, which is reverse product rule. You already learned it? Yeah. All right. So for this one, with U substitution, it's called U sub or integration by substitution. This technique was invented 300 years ago, and it's just brilliant. Whoever came up with this, I don't know, maybe it was Newton, is just amazing. And I don't know. You'll see like the fact that someone created this out of their brain is insane. All right, we need to rewrite this entire thing so it's something easier. Remember I told you before in math, if you can't solve something a certain way, then rewrite it so you can. So rewrite it to fit some other rule that you already have. So what we're going to do is we're going to rewrite this entire thing with u being equal to the square root of x. So that means this is substituted for, and this is substituted for. But we still need this right here, this dx. Okay, everything needs to be in terms of u. There is no implicit anti-differentiation, so you cannot mix variables. Everything that you look at right there, that square root, the e to the square root of x over x, the red, it has to be in terms of u. So we have to substitute everything in here so it's in terms of u. So we need to figure out what this dx is. Now this is where it gets really clever. How can I get a dx out of this? Where it's in terms of x and u. What can I do? You do know the answer, you just have to think about it. But the knowledge that you need is in your brain somewhere. You just have to put it together. How can I get a dx out of it? Yes?
Do you put it in front of it?
No, because it's part of that integral. You can't. No, that's a good question, but you can't. That's like saying d over dx and like, can you move the dx somewhere else? You can't. It means like derivative. So this means antiderivative. Yes. Exactly. That is crazy. Watch. She said you can take the derivative. Watch this. This is going to blow your mind. You can do the derivative of this, and look, a dx pops out. Look at this. So now I can solve for that dx. So let's multiply both sides by dx. Okay. And then you're going to have du is equal to 1/2. I'm actually going to rewrite this just so it looks like the problem above. So it's going to be 1/2, but I'm going to put the square root of x on the bottom because that's what this means. dx. Now check this out. What I'm going to do is I'm going to multiply both sides by 2. These cancel. Now this blue right here, this remainder part that I have for the blue, I'm going to highlight it. This thing right here, it's actually in the problem. It's right here and highlighted. Now watch this. This whole thing is equal to e to the square root of x, which is equal to u. So I'm going to put e to the u here, times that whole blue part that I highlighted is actually equal to 2 du, because it says it right here, 2 du. Look at how easy that is. Look at that blue on the right, the upper right. That's literally, you can do that. There's a rule for that. We have that rule. I mean, we just have to go backwards with it, of course. But that's insane. Like, think about that for a second. That is insane. What's the antiderivative of 2e to the u? Anybody? Just yell it out. People at home, just unmute and just yell it out. What's the antiderivative of 2e to the u? No. We did just do something similar to it. Not 2e to the u. What's the antiderivative? No. You got to just think for a second. Logan, you know it? You're close. The antiderivative is not 2e to the u. No, it's 2e to the u What? What'd you say? No. No. I showed you a comic about this.
Plus C.
Plus C. So you were right. I was just being mean. So it's 2 e to the u plus c. Okay? Now you don't actually need the plus c because we're finding the area. I just wanted to see if anyone would get that. You didn't do the plus c though. There's infinitely many antiderivatives. You just chose one of them where c is 0. Yes. Oh, I thought you were raising your hand. Sorry. Okay. We're not doing the we are doing the antiderivative, but we're just a little ahead. So I'm going to go backwards. If you wrote it down already, we're going to write it down in 2 seconds. All right. This 1 and this 4 is for x is equal to 1 and x is equal to 4. But we are in terms of u now, and this is where it becomes AP real quick. You need to make the 1 and the 4 in terms of u. So how can I make that x equals 1 and x equals 4 to be equal to u, in terms of u, I mean? Yes. Square root them. Because right here, u is related to x with the square root. The square root of x is equal to u. So you do the square root of 1 is 1. The square root of 4 is 2. You have to change that. And this is why I said it's an AP thing, because regular doesn't have to worry about stuff like this. Okay, but it's often forgotten about. If you look at the answer choices for this multiple choice, they'll have ones with 1 and 4 and 1 and 2, 1 and 16. They're trying to trick you. So don't pick those. Okay, now we can do that antiderivative that I was talking about before. You don't really need the plus c though, because we're doing the area. Oh wait, we're done. We don't even need to do all this. I went overboard. Okay, anyway, that's the answer. So which one is it? B? No. C. Okay, you could put the 2 in front, by the way. So if you look at C, they put the 2 in front. That's completely legal. It's kind of like if you do the derivative of 3x squared is equal to 3 times the derivative of x squared. That's perfectly legal. You can do that with antiderivatives as well. Okay, I thought we had to keep going further because usually we do, but this is kind of a weird like AP-esque problem, but this is the answer here. But anyway, don't forget the plus C is the moral of the story for what I was ranting about before. Sorry. But watch, you'll never forget the plus C now. You're welcome. Okay, is everyone still on board? Okay, whenever there's a substitution, 99% of the time, and I will show you the 1% time where it's not like this, the u is going to be the most buried function. So if you look at the original function here, that e to the square root of x over square root of x, the most buried thing is the square root of x. That's your u. AP tells you it's u for this problem. Sometimes they don't do that. They'll leave out the set u equal to the square root of x. You have to figure that out yourself. Okay, there's only 2 options for the u. It's either the square root of x or 1 over the square root of x. And if you try 1 over the square root of x, it will not work. Okay, never set e to u because e is not a variable. It's a constant. E is like 1 or 2 or 3, only it's way more special. So don't ever set, u equal to e, because it can only be e. It can't be u. Okay. How's everyone feeling here? Looking at your brain muscles here? All right, this next one's easy, thankfully. Oh. All right, so I need this translated in English from math. What does this mean here?
The function that defines 1 to 5.
So from 1 to 5, what are we finding now? Area. That means find the area of that function between the x-axis and the graph from 1 to 5. Okay? Now it doesn't say that. It doesn't say what's the area like it does for, if you go back the 2 problems here, it said what is the area? This one, it says what's the integral, and you have to know that that means the area. And we have to find the area of this. Okay, there's multiple ways of doing this. I'm going to show the easiest way first, and then I'll show you the more mathematical way second. Okay, first thing I'm going to do is sketch a graph of that piecewise function. It looks like it's only going to be in the first quadrant. Kind of like what I said before. AP likes to do that. Okay, 3 is the cutoff. If you forgot how to do piecewise functions, though, make sure you pay attention to this. So we're going Okay, what I'm going to do here is I'm going to graph 1, because we're not starting at 0, we're starting at 1. We're going to 5, but 3 is the cutoff for the piecewise. What I'm going to do is I'm going to make a little highlighted here to kind of make a little boundary. So this is a boundary of where the pieces shift. Okay, so the left side of that boundary, I'm going to just say y is equal to 2. So let me put a little, let's do it right here, 2. Okay, so now if I'm graphing this, it's going to be here all the way to here. That's embarrassing. Must be a hole. Okay. And then I'm going to graph that second piece. I'm going to use a different color, even though it's one function. And it's x minus 1. So by the time it gets to 5, it's going to be at a 4. So let's just say this is 4. And it's a line, so I'm just going to do that. Okay. Now what we're looking for, well, is everyone good so far? I know that's not the scale. It doesn't even look like it would hit -1 for the y-intercept. It doesn't matter. We're just trying to get an idea of what we're looking at here. Okay. If you do want to waste a lot of time trying to graph it out and make it perfect, AP wouldn't look at it anyway because it's multiple choice A and B. It's a time test. So why are you trying to make a graph perfect? You're not a machine. Okay. So what we're finding here is this whole area, this whole thing here, plus this whole thing here. Do we actually need any calculus on this to find that area? Why not? Yeah, it's the basic shapes, the simple shapes. Okay. We have what, a rectangle and a trapezoid? Okay. You can figure those out this way. Okay. If you do that, I highly advise actually writing like just like it's a regular shape. This is a 2 and this is 2. So then now you know this area here is 4. You'll see me do this a lot. Like whenever I find the areas, I like write it and then I circle it. That's just how I do it in my head. It works that way. This one here, I'm actually going to break down the trapezoid into a triangle and another rectangle here. So we have, this is still 2, and then this is 2. So this is going to be 4. And a square is a rectangle, in case someone's going to call me on that. This is going up by 2 here. So it's 2 times 2 divided by 2. So this is 2 as well. And then you can just add those up. Okay, so you get 10. Okay, that's one way you can do it. The only calculus is in the notation. So that integral from 1 to 5, there's no other calculus in there. So that translation piece, that is totally fine if you want to do it this way. Another way you can do it, and this is more mathematical, I would not do it this way because I feel like that was pretty easy, but you could do this. You can do the area is equal to 1 to 3 of 2 dx plus the area from 3 to 5 of x minus 1 dx. Now this is actually a really good problem to do here because it's a good practice of going backwards. So we are going to do it this way. So please write this down. I think it could help. Right, Hunter? All right, what's the antiderivative of 2? 2x plus c, right? By the way, if you remember when I was subtracting to find the area of this one up here, if you had a plus c, it would just be c minus c. So you never have to worry about the plus c with this, okay? If you remember right here, I subtracted when you plug in the 2 and you plug in the 0, the c's would cancel, so it does not matter if you include those or not. I wouldn't. But I forgot who said it, but the antiderivative is 2x. So what I'm going to write here is 2x, and we're integrating it from 1 to 3. So you put a 3 in there, you put a 1 in there, and you subtract. Awesome. Okay, what is the antiderivative of x? Just yell it out. X over 2, the derivative of x over 2 is 1/2. So you're on the right track. X squared over 2. Okay, that's called reverse power rule, what you guys just did in your head. What you do is you take whatever the expression is, you add 1 to it, and then you divide by whatever that power is. It will always be that way. So he said x squared over 2. That's why it's x squared over 2. Okay, and if you don't believe me, do the derivative of this. Okay, you bring the 2 down, you're going to have a 1 times x, and then 2 minus 1, you get x. You can always test it, and it's all the stuff you've already mastered from the first 3 units. Hey, what's the antiderivative of 1? X plus c, right? We don't need to worry about the plus c for this, though, so we're going 3 to 5. Okay, check this out here. So we're going to plug the 3 in. So you're going to get 6. Minus when you plug the 1 in, you get 2. I'm going to put it in parentheses. I know you don't need to. I just like everything organized. You plug a 5 in there, and you get 25 over 5, or 25 over 2. That's embarrassing. 25 over 2 minus 5. So that's the first part when you plug in a 5. Minus, then you're going to plug a 3 in there, so it's 9 over 2. Minus 3. You can see why this is way more complicated than what we did before. And you would get 8 minus 5, 3 minus 3, no, plus 3, plus 4 is 10, yeah. So yeah, that was 16 over 2. That's why I said 8. Minus 5 is 3, plus 3 is 6, plus 4 is 10. Okay. Obviously, this is not the fastest way to do it compared to graphing it, I think, but it was still good to go over all those rules. I shouldn't say all those rules. It was one rule, power rule, reverse power rule. Yeah. But just in case you were like, wait, how do those people know that the antiderivative of 2 is 2x? Well, one way you can do it is the derivative of 2x is 2. So now we're just going backwards. Okay, or you can do it this way. You have 2, it's x to the 0. Reverse power rule. Add 1 to the power, divide by that power. Now you get 2x to the 1 over 1, which is 2x. Okay, so that brings us to our next antiderivative rule. Make sure you write this down. Unless you already understood what I just said, you don't need to worry about it. But if you do the antiderivative of some constant, I can't use c, let's use a, of x to the n power with respect to x, it's going to be equal to a times x to the n plus 1. So you add 1 to the power instead of subtract. And instead of multiplying it, you divide. Plus c. And this is called reverse power rule, inverse power rule. Sometimes it's called power rule for integration. It's all the same thing. Yes. Cool. If I did something wrong, though, definitely tell me.
No, I suppose the x wasn't sandwiched like it said before, but then I realized it's equal.
It's sandwiched like that because it's Leibniz. He was the co-founder of calculus, even though Newton did it many decades before him, and that was the notation he used. My guess is because they were trying to show that it's the opposite of of derivative, so it's divided by dx. They multiplied both sides by it, and it ended up being at the end. So they just kind of kept it, but it is annoying. A lot of people think, oh, can't you just do like this? But no, you still need the dx, just because that's the notation. You cannot do it that way. You would get marked off on AP. So that means I would have to mark you off. Sorry. Questions on that one?
Are a lot of them going to be that simple with the graph?
Yes, these are from an AP test. Like I literally screenshotted them and threw them in here. So like these are all AP exact problems. So I'm throwing you exactly into what's on the test. So if you're like, this is so hard, like it is because it's the first time you're seeing it. If this is easy for you, then you should have taught yourself Calc 1 and went right to Calc 2 because you're wasting your time here. Okay, things to look out for when it's asking for area like this. If you graph it, you go, oh, that's linear and that's linear. These are both linear. That's going to be easy basic area. So that's like one thing that I would look at like in my head, oh, that's just easy. I don't even need to worry about the antiderivatives on this. It's going to be cake if I just draw it out. Okay, completely up to you. Uh-oh. What?
Can you just like if you're looking at these ones like this, and you're trying to decide if plus is going up or not, so you don't need to really use integration. You can just like, if it's x first, if it's not x squared, x cubed, then
Yeah, I literally just said it. If it's linear, No, I wouldn't pay attention to me either. I get it. Yeah, 2 is technically linear, even though it's a constant, and then x minus 1 is constant. Yeah, if it's squared, then it's crazy because now it's not a basic shape anymore because it has that curve to it. Okay. There are some instances, I'm sure that's what this person's commenting on right now, is what if it's one of those half circles, you know, the x squared plus y squared with conics, if you guys remember that from advanced algebra. Then yes, you can use a semicircle area as well.